Welcome to The Explainer. Today we're going to be digital detectives. We're going to uncover how machines learn to read, sort, and, well, understand the massive world of text that surrounds us. And we're going to do it all with a really clever technique called naive Bayes.
All right, let's kick things off with something you deal with literally every day. You open up your inbox, right? And somehow it's already figured out what's important and what's just junk. How in the world does it know?
Or, hey, think about a movie review site. You drop a comment like, unbelievably disappointing, and boom, it's instantly tagged as negative. How does a computer pick up on the vibe of your words, even with all the sarcasm and weird phrasing we use?
And get this same kind of tech can even solve historical mysteries. I mean, for centuries, people argued over who wrote 12 of the Federalist Papers. Then, back in the 60s, statisticians used these exact same ideas, just looking at word patterns, to prove with almost total certainty that it was James Madison.
So spam filtering, figuring out if a review is good or bad, even attributing authorship, all of these things fall under this big umbrella called text classification. It's really just the process of teaching a computer how to automatically slap a label or a category onto any piece of text.
So the big question is, how do we give a machine this kind of superpower? Well, you've basically got two options, the old way and the new way.
The old school method was to, build this giant maze of manual rules. A programmer would literally sit there and write out this huge list of if-then statements, kind of like what you see here. If an email has the word dollars and you have been selected, then yeah, it's probably spam.
But you can probably see the problem, right? This whole approach is super brittle. What happens when a spammer just uses the word prizes instead of dollars? You got to go back and add another rule, and another, and another. It's a huge pain. And that's exactly why the modern approach is to have the machine learn from examples. It's just way more adaptable.
And this table just lays it all out perfectly. A machine learning model can look at thousands, even millions of spam emails and just learn the patterns all by itself. It can scale up, it can adapt when the spammers change their game. A system of manual rules just can't keep up.
Okay, so let's get into it. Let's pop the hood on one of the most foundational and, honestly, effective text classifiers out there, naive Bayes. At its heart, this is all about probability.
It all kicks off with this elegant but super powerful formula, Bayes' theorem. Don't let the math scare you. All it's really doing is giving us a way to update what we believe when we see new evidence. For what we're doing, it answers a simple question. What's the probability this email is spam, given the words I'm looking at right now?
Yeah, let's stick with that detective analogy. Think of it like this. The prior is your initial hunch. Before you even look at the email, you might guess that maybe 1 in 10 emails are spam. The likelihood, that's your new clue. How often do words like winner or free pop up in emails you already know are spam? And then the posterior, that's your final conclusion. It's the updated probability that this specific email is spam now that you've seen the evidence.
Okay, now for the most important part, the naive in naive Bayes. This is the big shortcut, the clever trick that makes it all work so fast. We make this huge, simplifying assumption. We pretend that every single word in a sentence is completely independent of every other word. Now, we know that's not true in real life, right? New is very likely to be followed by York. But by treating each word as a totally separate clue, the math becomes way easier. And the crazy part is, for a ton of problems, this naive shortcut works surprisingly well.
But of course, computers don't speak English, they speak math. They need numbers. So we have to turn our text into numbers, and we do that with something called a bag of words model. Just imagine taking all the words from an email, ignoring the grammar, ignoring the order, and just dumping them into a big bag. Then we make a master list of every unique word we've ever seen, and for any new email, we just count. How many times did free show up? 2. Winner, 1. That simple list of counts, that's what the computer actually works with.
Okay, so the theory sounds pretty solid, right? But, and there's always a but, when you try to use this in the real world, you run into a couple of really nasty mathematical traps, and we need to know how to get around them.
So imagine this, you've trained your model on thousands and thousands of spam emails. It's getting pretty good. But then a new email comes in and it has a word the model has never ever seen before in a spam message. Let's say the word is blockchain. So what happens? Well, the probability of seeing the word blockchain in a spam email is 0. And because our naive assumption means we have to multiply all the probabilities of all the words together, that one single 0 just torpedoes the whole thing. The final probability for that email being spam becomes 0.
no matter how many other spammy words are in it. 1 0 ruins everything.
The solution is a really elegant little trick called Laplace Smoothing. It's also called add-one smoothing. All we do is we just pretend. We pretend we've seen every single word in our entire vocabulary at least one extra time. By adding 1 to all the counts, we make sure that no probability can ever be exactly 0. And just like that, our calculation is saved.
All right, we dodged one bullet, but there's another one. Think about it. Probabilities are always small numbers, right? Decimals between 0 and 1. When you start multiplying hundreds or even thousands of these tiny little decimals together, the final number becomes so ridiculously small that a computer's memory just can't handle it. It's like it rounds down to 0. This is a classic problem called numerical underflow.
And the solution here is another beautiful math trick. Instead of multiplying all those tiny numbers, we take their logarithms and just add them instead. It's a basic property of logs that adding logarithms is the same as multiplying the original numbers. This keeps all our values in a nice, stable range that a computer can handle. So we turn a fragile multiplication problem into a nice, sturdy addition problem.
All right, so we've built our classifier, we've debugged the common problems. Now for the final scorecard. How good is this thing really? What are the pros and cons?
So here's the bottom line. On the plus side, naive Bayes is ridiculously fast and efficient, and it's fantastic when you don't have a ton of data to train on. But the big con is that core naive assumption we talked about. Because it ignores word order and context, it can get tripped up by more complex language. So on really large, messy datasets, more modern models will usually beat it.
And when we talk about success, we need to go deeper than just how often was it right. We need better metrics. For something like a spam filter, precision is key. It asks, of all the emails we called spam, how many were actually spam? You want that to be super high, because you do not want to lose an important email. Then there's recall. That asks, of all the spam that actually exists, how much of it did we catch? The F1 score is just a way to blend those two ideas together, giving us a single number that tells us how balanced our model is. It's about finding that sweet spot.
And that really leaves us with a final question, doesn't it? In this age of massive, billion-parameter AI models that cost a fortune to train, what can we learn from a simple, even naive idea like this? Well, I think naive Bayes is a powerful reminder that sometimes elegance and a clever shortcut can be more effective than just raw computing power. It's a beautiful piece of evidence that understanding the fundamentals is what really matters, and that sometimes the simplest tools are the most powerful ones.